Hi everybody! So we're going to go through our last set of vocabulary words that are going to be new words in this chapter, and these are about what are called extreme values of functions. Now when you hear the word extreme, you probably think like super awesome or like super on the edge of ridiculousness, which is basically what extreme values of functions are. Extreme values of functions are just high points and low points, so places where the y values reach high points and low points. We have what are called local or relative extremes. We can have local or relative maximums or minimums. We also have what are called global or absolute extremes. So let's start with local. The local maxima occur where the graph of a function has a peak or at an endpoint. And the endpoint has to be closed in order for there to be a maximum there. The local or relative, well, let's do an example for this one. So for the local maxima on this graph, they would occur here, here, and here, because those are all places that are high spots for their little section of the graph. They're at the top of a mountain. So that would be where x is 0, 4, or 7. If we look at this other graph, the local maximum occur here, here, or here. So when x is negative 1, 2, 3, 4, 5, 0, or positive 4. This time there were no extrema at the endpoints because those have arrows. They're not closed endpoints that stop there, they keep going. The local relative minima occur where the graph of a function has a valley or at an endpoint. So for example, the local minima of this graph would be here and here. So at x equals 1 or 6. The local minima of this graph would be here or here. So at x equals negative 3 or 2. Now we would not have minima at the arrows because again the graph doesn't stop there, it keeps on going. So you can't be a minimum if you never stop going down. The global or absolute maximum is where the graph achieves its highest y value over a given domain. A function does not always have a global maximum because sometimes a function goes upwards forever. So we have to just really look at the graph that we have and determine if this exists or not. If we look at this first graph, the global maximum would be at this endpoint, because that's the highest the graph ever goes, and we know that because it's got dots or closed circles at the endpoints, and so that would be at 7. In this graph, the global maximum would be here because that's the highest the graph will ever go. Even though the graph doesn't stop on the ends, it has arrows, they're both pointing down, so it's never going to go up higher than this point. Last but not least, we have the global minimum. A global minimum occurs where a graph achieves its lowest y value over a given domain. We do not always have to have a global minimum. It just depends on the picture. In this first picture, the global min would be here because that's the lowest the graph is ever going to go, is at x equals 1. In the next picture, the global min would be none. Because since these arrows both point downwards, it's going to be going down forever, and so we're never going to stop. We're never going to reach our lowest value. An extreme value can occur at an x value where y prime equals 0 or y prime, not y double prime, I'm sorry, where y prime is undefined, or at an endpoint as long as it is a closed endpoint. So how can we use that to help us figure out how to calculate these values? Well, let's take a look at some examples. Option number 1 is to make what's called an options list. you are going to choose this option, this method, if you have a function with a specific domain. So for example, if I say you're given this function and a closed interval between 0 and 3, identify the location of and classify all the extrema. So the first thing we would do is take the derivative, because we know that extreme values will either occur at the endpoints or where the derivative equals 0, at maxima or minima. The derivative of negative x would be -1. The derivative of e to the something is just e to the something, but I would need to multiply by -1 because of chain rule. So this derivative simplifies to -1 plus e to the 1 minus x. So first we would take the derivative. Then we would make our derivative equal to 0. So to solve this, I would have e to the 1 minus x equals 1. I'm just moving the -1 over. I would natural log both sides. And the natural log of e and e cancel, so we just have 1 minus x. The natural log of 1 is 0, which is an important fact to remember because we're going to need to know that frequently. Finally, I would add the x to the other side, so I would have 1 equals x. So my critical point in this problem would be at x equals 1. Now, because we know that all extreme values must occur either at the critical points or at the endpoints, we would make a chart of values where we can see the x value and the y value, which we're going to call f of x, at the endpoints and at the critical points. This is what's called the options chart. Now your options would be 0, 1, and 3, because these are the endpoints and the critical points. Now what we want to do is calculate the actual y values so that we can see how high or how low these values go. So if I plug 0 into the original function, I would have 0 minus e to the 1. So it would just be -e. If I plug 1 into the original function, I would have -1 minus e to the 0. Now e to the 0 is 1. So I would get -2. And if I plug 3 into the original function, I would have -3 minus e to the -2. Now without a calculator, it's going to be very hard to simplify these, but I can still tell which ones are big and which ones are small. -e is approximately -2.71828. -2, and then -3 minus 1 over e squared is definitely going to be more negativer than -3. It's going to be -3 point something. So if I look at all of those y values, I notice that my y value starts off at -2.718. Then it becomes -2, which is bigger, so the y values go up. And then from -2 to -3, they go down again. So if you visualize that on a graph, it would look like this. The y values go up and then the y values go down. What that means is that this middle value right here must be the maximum. And we know actually that not only is it a local maximum, it is also the absolute maximum for this section of the graph. Because based on this picture that I drew, it never turns back around. So the local and absolute max would be at x equals 1. Now the minimums would be at the two endpoints, but since -3 is lower than -2.71828, we would say that there's a local min of negative 2.71828 at x equals 0. And we would say that there is a global min of negative 3 point something at x equals 3. So if you have a closed interval, you just look at your possible y values and determine which one's the biggest, which one's the smallest. Option number 2 is to look at the first derivative. You're going to use this option when there's a function with an infinite domain, or if you have the graph of f prime. So here's what this says. This says that if f prime changes sign from positive to negative at a specific x value, then f has a local max. So let's say we pick this c value. If f prime, which means the slope, changes from uphill to downhill at this number, there must be a max there. If f prime changes signs from negative to positive, so if it's going downhill and then uphill at this number, then there must be a min. And if f prime does not change signs, so if you're going uphill and then you continue to go uphill even though your slope reached a value of 0. An example of this kind of graph would be like x cubed, which looks like this. The slope would be 0, it's just that you go uphill on both sides, then there's not a max or a min there. So for example, if I give you the function f of x and say identify the location of and classify all of the extreme values, here's what you would do. First, you would take the derivative, because we know that extreme values happen at places where the derivative is 0 or at endpoints. So we would take the derivative, which is 8x cubed minus 8x. We would make the derivative equal to 0. So we would factor out an 8x. We would continue to factor. And we would get x equals 0, negative 1, or 1. Then we would make a chart and we would look at the sign of f prime. So we would have negative infinity, negative 1, 0, 1, and infinity. If we now look at the sign of the derivative, if I pick a number less than negative 1, like negative 2, and I plug it into the factored version of my equation, I would have a negative, and another negative. 3 negatives make a negative, so my graph is going downhill. Between negative 1 and 0, like negative 1/2, I would have a negative, a positive, and a negative. 2 negatives make a positive, so my graph is going uphill. Positive 1/2, if I plug that in, I would have positive, positive, negative, so negative would be going downhill. And bigger than 1, like 4, I would have positive, 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 positive would be going uphill. Based on the sign changes in this graph, at first the graph changes from going downhill to uphill. So this is going to be a min. Then the graph changes from going uphill to downhill. So this is going to be a max. And then the graph changes from downhill to uphill again. This is going to be a min. You can literally visualize it by looking at the picture. So we would say f of x has a min at x equals negative 1 and x equals 1 because f prime changes from negative to positive. We would also say f of x has a max at x equals 0 because f prime changes from positive to negative. Now you'll notice I needed to write an explanation here. It is standard policy that in AP Calculus, if you're using the first derivative to identify maxima and minima, you cannot just assume that whoever's grading your paper understands this chart. You may make the chart, but when you actually state your answer, you have to use words to justify your answer. So writing this explanation, because f prime changes from negative to positive, or because f prime changes from positive to negative, is required. Now the reason that neither of the endpoints here have a max or a min, even though it looks like this would be a max and this would be a max, is because it never stops. This graph continues, and you can only have a max or a min if it actually stops. Let's take a look at another example. Given the graph of f prime, identify the location of and classify all of the extrema. So this is f prime's graph. Oops. So we are looking for places where f prime equals 0. This graph equals 0 here, here, and here. So first, we consider the places which are really the x-intercepts, the places where f prime equals 0. At this first stop, the graph changes from below the x-axis to above. So that means the derivative is changing from negative to positive. So I would state f has a, and we would call this a min, at x equals negative 1 because f prime changes from negative to positive. If you want, if it helps you to sketch a little picture, because this graph starts off below, the first part of the original function would have been going downhill. Then the graph switches to above, so the next part of the original function would have been going uphill. Then the graph switches to below, so on the original it would have been going downhill. Then the graph switches to above, so it would be going uphill on the original, and then it would stop. Now there's another place where f has a min. The second place where f has a min is at x is positive 1, because that is another place where the graph changes from below to above. So x equals 1 would be another place. The last maxima or minima that we get from the x-intercepts is at 0. Here the graph is switching from above to below, so from uphill to downhill, which means f has a max at x equals 0 because f prime changes from positive to negative. Now, in addition to considering the places where f prime equals 0, the second thing we need to consider are the endpoints. And this is another place where I think kind of sketching a picture of what the original would look like helps. So this little graph down here would be the original based on this derivative. It doesn't really matter what the y values are, it just kind of matters what shape it is. So it would go downhill, uphill, downhill, uphill. Because this first endpoint is an arrow, which means this graph goes on forever in that direction, there is no max or min. But the other one is a dot, it stops. Based on the way this picture looks, it stops at the top of a hill. So that means that I would say that f has a max at x equals 1 because it is an endpoint. When we have an endpoint and it's a max or min, you don't really have to justify your answer. You can just say because it's an endpoint. Okay, now you'll notice that there is a third option. So the third option is to use the second derivative. You only use this option if you have a function and you are checking whether a specific x value has a max or a min. So for example, it might say, if you have this function, do you have a max or a min at x equals 1? It's not saying like in general, it's saying at this specific number. So here's what it means. In order to use the second derivative test, it should actually be called, in my opinion, the combo test, because you actually need to combine the first and the second derivative. So here's what this test says. If the first derivative at your x value is equal to 0, and the second derivative is greater than 0, then your graph must look like this. The second derivative being greater than 0 means you're concave up. The first derivative equaling 0 means you're right at the bottom. So this would be a min. If your first derivative equals 0 and your second derivative is negative, then that means you're concave down and you must be right at the top. So this would be a max. So here's an example of how you would use this. Given this function, do we have a max or a min at 1? First, let's check out what the value of the first derivative is. The first derivative of this function would be negative 1 minus e to the 1 minus x times negative 1 because of chain rule. So I would have negative 1 plus e to the 1 minus x. If I evaluate this at 1, I get negative 1 plus e to the 0, which means I get negative 1 plus 1, which is 0. Oop, you can't see what I wrote. I'm sorry. If I now calculate the second derivative, so I've confirmed my first derivative equals 0. If I calculate the second derivative of this guy, I get the derivative of negative 1 is 0. The derivative of e to the something is e to the something, but times negative 1 because there's a chain rule. So I have negative e to the 1 minus x. The value of the second derivative at 1 would be negative e to the 1 minus 1, which is negative e to the 0, which is negative 1. Well, the first derivative is 0, which checks off this one and this one. But the second derivative is negative. If my second derivative is negative, I'm concave down, so I must have been right at the top. So f has a max at x equals 1, and here's how you justify this answer. Because f prime of 1 is 0, and f double prime of 1 is negative or less than 0. Again, writing a sentence here isn't optional. You do have to justify your answer by AP standards. All right, thank you guys so much for watching. I know this was a longer video. It was kind of a lot to talk through because we have so many different choices about how to do these problems. We will definitely spend some time going over this in class tomorrow. Have a wonderful afternoon.